Hello guys, I'm Chenagala Sonith, and this is an IAT Tech Talk. I'm from CSC Data Science and my roll number is 2195186 And my topic today is using quantum technologies to improve fiber optic communication systems. These are fiber optics. These are yeah, sorry, yeah, abstract. Let's first get to the topic at hand. Abstractly, recent developments in quantum technologies can have in the field of fiber optic communication systems the ability to generate, manipulate, transmit, intercept, and signal over the cheap photons and open new routes that can trigger a completely new generation of communication systems. We show that quantum technologies can address two of the more challenging problems communication engineers face nowadays: capacity and security. Indeed, by radically increasing the number of photons used to encode each bit of information, we can more efficiently explore the full capacity to carry information of optical fibers. Moreover, by encoding information in individual or very few photons, we can take advantage of the quantum layers to add new functionalities to communication systems. Secrecy is the more obvious one, but a completely new set of functionalities can be added at the physical layer, considering the peculiarities of quantum laws that rule transmission and detection. And so the introduction to the topic, quantum physics theory was developed in the first two decades of the 20th century in an endeavor to understand the fundamental properties of matter and its interaction with electromagnetic radiation. Electromagnetic radiation. Electromagnetic radiation. In the second half of the 20th century, quantum theory led to some technological realization through the invention of solid-state resistor, the laser, and optical amplifier. Despite the huge impact these devices have in communication and information systems, quantum theory is still only primarily addressed in most engineering schools. Despite the huge impact these devices have in communication and information systems, quantum theory is still only primarily addressed in most engineering schools. However, micro and nano ouch. However, micro and nanotechnologies are also rapidly evolved rapidly, and nowadays it is possible to manipulate quantum systems quite easily. Quantum key distribution systems, or QKD systems, is the first commercial communication systems to explore the laws of quantum mechanics and provide new functionalities. The underlying principle of QKD is that nature prohibits the gain of information in the state of a quantum system without disturbing it, which can be used to provide unconditionally secure distribution of secret keys. Increasing transmission capacity. The widespread deployment of the fiber to the home, broadband internet connections, and online video gaming in video and gaming is increasing substantially amount of traffic in core networks. So if everyone asks for a network, where will they give? It will cause traffic, and then like you become overloaded. So to cope with this increasing amount of traffic, operators have been increasing the bit rate per channel and the number of optical channels per fiber. In this section, we review the capacity limits of classical fiber optic communication systems and analyze how the encoding of information in single or very few photons can allow us to go beyond classical limits. Transmission capacity limits. A classical receiver is a device that receives a classical signal, typically an electromagnetic field, current, or voltage. And extracts information from that signal. In a fast-time digital transmission system at the emitter and the signal is modulated in order to generate symbols at a constant symbol rate. The emitter during transmission and even at the receiver, noise is added to the signal, which means that part of extracted information is meaningless because it is generated by the added ones. Therefore, in order to calculate the maximum amount of information that can be transmitted, you have to calculate the maximum amount of information that can be extracted from the signal with noise and then subtract the information generated only by the noise. So this is the formula. C equal to B log base 2 1 plus S by N. Here S is average signal and noise uh, O and N is noise energy per signal and B is channel bandwidth. Okay. So okay. So according to the diagram that was there, the okay, let's show that. So this is a diagram in it. So yo, so this is the diagram. So this graph represents spectral efficiency this way, right? Spectral efficiency varies. And what x-axis it has input power per optical channel. So what is the graph about? What is the graph about? Spectral efficiency levels for 2000 kilometer long dense wavelength division multiplexing system with 100 optical channels separated by 50 gigahertz. Spectral efficiency is a measure of the transmission capacity per spectral bandwidth. We are assuming 25 fiber spans. Between each fiber span, there is an optical amplification module that completely compensates for fiber losses. The noise figure of each amplification scale is 4.2 decibels, and the fiber losses are assumed to be 0.2 decibels per meter. Right. So this is the limit, that is linear Shannon limit. This is the limit, guys. And next one. So in the figure one, the fuse effect is sorry. In the fuse effect limit is represented as a straight vertical line indicating that there is a maximum amount of optical power a fiber can handle. Sorry, fiber can handle. There you go. After which the fuse effect is ignited and the fiber is permanently damaged. In fiber optic communication system, this value tends to be quite small, that is closer to 1 volt, almost equal to 1 volt due to the presence of several connectors and narrow bands in the fiber. In order to increase the power efficiency of next generation fiber optic communication systems, that is, in order to increase the number of bits carried per photon, you need to you have to be able to generate, manipulate, transmit, and detect single or very few photons. This requires quantum sources and receivers. Engineering single or few photon transmission system. Wait a minute. Yeah. So the next topic is engineering single or few photons transmission systems. True single photon sources, typically known as an on-demand sources of photon guns, are still quite complex to realize, since most of them demand cryogenic temperatures or only operate in a vacuum. So they are very tough to get or operate because the conditions that in which they operate are very hard to obtain. So they are not that feasible or viable to use. Typically, these single photon sources use an external control system such as a laser to put a quantum system in its excited state, which is going to emit a single photon during a relaxation process. Wait a minute, guys. Yep. Uh, I was there. Typically, these single photon sources use externally controlled systems such as lasers, but quantum systems in excited state which is going to emit a single photon during the relaxation process. Examples of quantum systems using single photon sources are single atoms and molecules, single ions, color centers, quantum dots, and quantum belts. Oh yes, let's go. Although this kind of source allows us to obtain two single photons, they also demand the manipulation of very complex systems, usually involving complex free-space optical alignment systems. Yes, these sources are difficult to implement and not easily integrated with other components of the communication system. A different approach to obtain single photons is based on the generation of time-correlated photon pairs in a non-linear medium. In this case, one photon of the pair signals errors in the presence of the other photon. These sources are known as heraldic single photon sources and are based on translator and nonlinear medium. Due to a nonlinear process, typically spontaneous four-wave mixing in optical fibers, two photons from the complexer are annihilated and two photons are created in symmetrical frequencies around the complexer such that the net energy and momentum are conserved. Although some applications in the field of quantum information demand single photon sources, there are other applications that require only weak coherent light fields. In that case, a highly accentuated laser can also use as a source of two photons. Yep, let's go. What do you mean, guys? On this? So next one is introduction to new functionalities of this quantum mechanics, random number generation and key distribution. True random numbers are hard to generate. Indeed, any random number generated based on a classical system should be as predictable as the Lighting theory is predictable. Nevertheless, despite the deterministic nature of classical physics, it is possible to build complex classical systems with such a large number of degrees of freedom. The future behavior of the system is almost unpredictable. However, if we wish to go further and obtain a perfect random number generator, we have to base it on the quantum system. The system described by quantum laws that are probabilistic by nature. Another important application of quantum random number generators is quantum key distribution. QKD is nothing more than a synchronous continuous generation of random numbers at two distinct locations. Both numbers in one in each location are indeed the same random number that is going to be used as an encryption. Excuse me for this. Yeah. Quantum entanglement can be used to generate pairs of random numbers at two different locations. pair of entangled photons, the pair of photons described by the same wave function. The wave function that cannot be factorized into two independent wave functions, one for each photon, no matter how far apart the photons are. This means that the pair is in the photons is created and sent to two different locations, and measurements are performed in one location and the measurement is performed in the photons of the pair. The result of the measurement is completely random. Different approach to QKD is based on generation of a random number in one location and subsequently the transfer of that number to a different location, making sure that it is impossible to gain any relevant information about the generated number between two locations. In these systems, which are already commercially available, quantum laws are explored in the presence of each topic, or better put, quantum laws are used to quantify the amount of leaked information between two locations. Then privacy amplification is applied to guarantee that even with all the leaked information, it is not possible to obtain any relevant information about the verified random number, that is, about the key. This quantification of the leaked information is only possible due to the non-clonal theory, which forbids the gain of information about a quantum unknown system without inducing a perturbation in the system. So this is a diagram, an example of a layer 2 encrypted point-to-point link in which QKD is used to continuously generate new encryption keys. The frequent and continuous change of keys makes it virtually impossible to break the classic encryption code. There are already QKD systems in the market that allow a change of encryption keys every minute. This also applies to cryptocurrencies or blockchain, where the keys keep changing every minute so that you do not encrypt them with any possible algorithm. So the last topic is quantum internet and computers. So we can use quantum technology for internet also. Like quantum routers are essential elements in the future quantum internet. Typically, a router uses a control signal, a packet header, to determine the output port. However, at quantum level, if we read packet header of a signal, it will destroy its quantum state. To overcome that, an optical router cable of routing photons without disturbing the quantum state is proposed recently based on polarization entangled photon pairs. So, the conclusions for today's tech talk are: in this article, we have identified two major problems in today's fiber optic communication systems: capacity and security. A possible solution for both problems can be found in the use of a very low number of photons per symbol. In that regime, the communication system is governed by quantum laws. The realities of quantum laws can be used to add functionalities. There are already commercially available products that explore quantum laws to add new functionalities, such as QKD systems and quantum random number generators. Nevertheless, most of the desktop most of the more disruptive technologies still remain only in the laboratory domain, such as quantum repeaters, quantum memories, uh, quantum routers, and quantum computers. These systems can be materialized in some practical devices. A fully functional quantum internet can start to emerge. It is clear that there are many exciting prospects for further development of quantum-based technologies, and certainly these developments are going to shape a future in communication networks. Thank you. I'm Sonith Yadav, and this has been my tech talk about use of quantum technologies in optical fiber.